A bubble could already be racing toward us at light speed. You would never see it coming or feel a warning. It is a quantum phase change called false vacuum decay. That means the fabric of our vacuum can suddenly switch states. Think soda freezing all at once, but for the entire cosmos. The basic idea is strangely simple and brutal. Our fields sit in a high-energy groove, not the lowest. A tiny bubble can tunnel to a deeper groove, then expand. The wall sweeps out at nearly light speed, rewriting physics. If that happens here, chemistry ends and so do we. The odds tonight look absurdly small, so breathe easy. We can still explore what it means without panic. This story is wild and it is real physics. And the twist is, the math suggests we might be safe. Start with an empty room stripped of air and light. Quantum fields still ripple there like sea swell after storms. Vacuum is not nothing, it is the lowest energy arrangement. Sometimes that arrangement is only a perch, not the floor. Physicists call that perch a false vacuum, a metastable state. Metastable means stable until a rare escape suddenly happens. Picture a marble resting on a tabletop with a hidden drop. It sits fine for ages, then tunnels through to a lower level. That tunnel is quantum and it needs no push. When it happens, a tiny seed of the lower state appears. It is the bubble, a pocket where the vacuum has changed. The surface around it is a wall of concentrated field energy. Why care about this at all, beyond sci-fi dread? Because the vacuum sets particle masses, forces, and every rule. Switch the vacuum and the rules switch with it everywhere touched. The mechanism is cold and it is very fast. The bubble starts subatomic, then grows as fast causality allows. The wall converts stored vacuum energy into a rushing front. Nothing inside can outrun it, not light, not information. A city would not crumble, it would simply stop existing. Numbers help anchor this weird idea and calm fear. In many models, the lifetime is astronomically, almost comically long. Think beyond 10 to the power of 100 years, and that is a conservative, order of magnitude way to speak. So yes, the phenomenon is real, but panic is optional. Zoom in on the wall where old and new vacua meet. It is thin on cosmic scales, yet intensely, violently energetic. Across that skin, constants can shift by tiny fractions. Those shifts can change chemistry, nuclear stability, and light itself. Outside rules persist until the front arrives and sweeps through. The wall speed pushes the limit set by relativity itself. That means no warning from ahead of the front. Inside, the new vacuum relaxes and releases difference as heat. How thick is that wall in practical units really? In many field theories, it is microscopic, far below centimeters. It could be near nuclear scales or even smaller. Such uncertainty is honest because we lack the true theory. Still, the action is clear enough to picture cleanly. Imagine dew racing across glass but driven by quantum energy. The dew edge is the wall, sweeping across an old phase. The front also drags matter and compresses it into a shock. A passing front would dump unimaginable energy in a blink. Estimates vary widely, from supernova levels upward per planetary slice. Yet there is no fireball, just instantaneous rule replacement. That contrast feels eerie and perfectly in character for quantum fields. One instant you check a message, the next the rules change. There is no pain, no ash, only absence where we stood. Here is why this enters real particle physics, not horror fiction. The Higgs field gives mass to elementary particles, including ours. Its measured mass is about 125 gigaelectronvolts, surprisingly light. Combine that with the top quark mass, near 173 gigaelectronvolts. Run the equations upward, and the Higgs self-coupling can dip negative. Negative means the current valley may hide a deeper one. That tipping scale may sit near 10 to the power 11 GeV. This is a rough place, blurred by measurement uncertainties. Change the top mass slightly, and stability can return. Add new physics above LHC energies, and stability also returns. This matters because we actually tested collisions at the LHC. Those energies are tiny compared with that distant instability scale. Also, cosmic rays reach about 10 to the power 20 electronvolts. They have struck stars and planets for billions of years. If collisions could trigger decay, we would not be here. The key point is subtle and honestly calming. Nucleation depends on the vacuum itself, not smashing particles together. Triggering requires tunneling across the whole field configuration. A lab event cannot arrange that global, coordinated transition. Even micro black holes would not change that basic story. We can still search for clues in the cosmic background. If inflation began in a higher false vacuum, bubbles could collide. Such collisions might leave faint round fingerprints in the microwave sky. So far, surveys see nothing conclusive, just noise and wishes. Could anything out there nudge the vacuum off its perch? Black holes tempt that thought because gravity bends fields strongly. Calculations show curvature can lower the tunneling barrier near horizons. For evaporating black holes, that effect could, in principle, matter. Yet the rate looks tiny, and astrophysical holes barely evaporate. Stellar holes absorb energy, they do not radiate much away. The universe has not sprinkled us with new holes recently. Even primordial holes, if they existed, are rare or gone. Cosmic rays remain our best natural stress test by far. One event reached about 3 times 10 to the 20 electron volts. They have been firing for billions of years, across vast volumes. Nothing triggered, so the hazard looks even more remote. High-energy colliders stay deeply below these natural bombardments. They also localize energy in tiny regions, not cosmic patches. Vacuum decay does not care about local sparks, only global tunneling. That is why safety reports land on cosmic ray evidence. And they were right, empirically, after many operational years. Meanwhile, theory keeps tightening the story with better calculations. The decay rate depends exponentially on action, a very steep sensitivity. Small tweaks in couplings swing the lifetime across ridiculous ranges, so our ignorance leans toward safety, not toward sudden doom. What would the inside be like after the wall passes? The honest answer is unreachable because no signal escapes out. Still, physics lets us outline likely possibilities with restraint. If constants shift, atomic structure could fail to hold. Hydrogen might be unstable, or chemistry could simply collapse. Even if atoms survive, star burning could change or halt. Gravity would keep curving space, but light might behave differently. Time would still flow, although its scale might resettle. None of that returns to us because causality blocks messages. Yet ideas like this power inflationary cosmology with real success. During inflation, a high vacuum drove rapid, accelerating expansion. That process likely ended through decay into a lower state. Our observable universe may be a bubble from that ending. Some models predict rare collisions between neighboring bubbles. Those could leave circular hot or cold bands in the CMB. Teams have searched maps with sophisticated statistics for years. So far, the skies stay quiet within current sensitivity. That quiet sets limits and it guides future detectors. Meanwhile, the concept keeps anchoring frontier questions responsibly. It is speculative, but it rides alongside measured, working physics. Paradoxically, the safest apocalypse is also the cleanest one. It leaves no smoke, no rubble, just a new rulebook unfolding. How likely is an event here within any human timeframe? The numbers favor patience beyond any normal comparison point. The decay rate is often written as a hazard per volume. That hazard combines a huge exponential suppression with unknown constants. Plugging conservative inputs gives lifetimes like 10 to the 100 years. Push parameters slightly, and you get 10 to the 1,000 years. Those are cartoonish scales, but they reflect real math. Even at those scales, infinite time still births rare events. In an eternally inflating cosmos, some bubble forms somewhere eventually. Expansion complicates the picture because safe regions keep growing. A bubble only threatens places it can physically reach. Our observable patch is finite and also racing away. So the chance here in the next billion years stays tiny. It is not zero, but it is effectively zero for us. Meanwhile, instruments keep checking the inputs we actually measure. Better Higgs and top masses will sharpen the vacuum map. If new particles exist, they could stabilize everything completely. The takeaway is simple and honestly merciful. We get wonder without urgency and science without doomsday dread. Use that freedom to ask sharper, more beautiful questions. Tonight, a bubble could rush unseen and we would never know. But the numbers say sleep, not scramble, and carry curiosity. We live in a universe where nothing is truly nothing. Where fields set everything and sometimes flirt with deeper states. I love that this threat teaches humility, not terror. It ties kitchen physics to cosmic history in one idea. Soda freezing, marbles tunneling, and galaxies all share rules. If you enjoyed that mental bridge, keep walking with me. I make videos that unpack wild concepts with calm clarity. Tap subscribe so the next strange story finds you first. We will visit black holes, neutrino fog, and time's hidden gears. And we will keep the math honest and the vibes human. Thanks for watching and for staying curious under this sky.